In the last lecture, we were starting our discussion of transport in curvilinear coordinate systems. Curvilinear coordinate system is one where surface of constant coordinate is a curved surface. As I explained last time, in the case of a Cartesian coordinate system, the surface of a constant coordinate is a flat surface. Z is a constant on surfaces which are flat. And because of that, the differential volume that we had constructed, it is bounded by flat surfaces, and the surface area of opposite surfaces is the same. When we are solving problems for the flow in a pipe or the flow around a spherical particle, for example, the surface of the boundary condition has to be applied on a curved surface. The surface of the pipe which is a cylindrical surface for the flow in a pipe, for example, or the surface of the sphere, which is a spherical surface. And if we express these in a Cartesian coordinate system, the expressions for the surface are rather complicated. As we saw when we discussed unidirectional transport, it is easiest if the surface is a surface of constant coordinate, because we can just apply the boundary condition on that surface of constant coordinate. Whereas in the case of curved surfaces, the expression for the boundary condition in terms of Cartesian coordinates becomes complicated. Therefore, we had discussed for a cylinder, for example, the surface is a constant coordinate surface, has a constant distance from the axis. So, rather than taking the distance from a plane as the coordinate, we took the distance from the axis as the coordinate, which is r for a cylindrical coordinate system, where the axis is along the center of the cylinder or the pipe. There are two other coordinates, the axial coordinate z, which is along the axis, and then there is a third coordinate, which is the angle around the axis. For the present, we will assume that it is axisymmetric. That means there is no variation with respect to angle around the axis. So, the variation in the temperature, concentration or velocity field is in the axial direction, in the radial direction alone, not in it does not vary as you change the angle around the axis. A differential volume, bound between two surfaces of constant coordinate, inner surface at r, outer surface at r plus delta r. The surface area of the surface at r is 2 pi r times delta x, where delta x is the thickness in the axial direction, where delta x is the thickness in the axial direction, and delta r is the thickness in the radial direction for this differential volume. So, this is an annular differential volume between two cylindrical surfaces that we are considering. Recall that balance equations are obtained by considering a differential volume between surfaces of constant coordinate. In this particular case, the coordinate, which is the distance from the axis, is a constant on cylindrical surfaces. Because of it is a cylindrical curved surface, the surface area at r and at r plus delta r are in general different. And you substitute that into the balance equation for the change in energy in a differential volume in a time delta t, energy in, energy out, and the production rate of energy produced per unit volume per unit time. These were the different terms in the conservation equation. Divide by volume, divide by time, divide by 2 pi r delta x, and divide by delta t. The factors proportional to r plus delta r and r do not cancel out, because the surface areas are different, at the surface at r and the surface at r plus delta r. And you substitute that in, and you get an equation in which there is the radial coordinate, the flux, instead of having just the derivative of the flux, you have 1 over r d by dr of r times q r on the right side with the negative sign, plus the energy source. Okay. And on the left you have the change in energy in temperature per unit time times rho Cp. And Qr is equal to minus k partial T by partial R. The thermal conductivity times the difference in temperature divided by the distance travelled. Okay. So, that is the heat flux in the radial direction with a negative sign because heat is transferred from higher temperature to lower temperature. And then I had substituted that in and got these expressions, okay, for the temperature field for in terms of the temperature grade in terms of the temperature, and for the special case where the density and the specific heat are constants, I can take that in and I will get this expression. And if the thermal diffusivity is also a constant, this is the expression that I will get. Okay. So, therefore, this additional operator that we get either for the temperature field or the concentration field, this more complicated form of the operator emerges because I am considering a differential volume whose surfaces, opposite surfaces, do not have equal surface areas. Okay. The opposite surfaces at r and r plus delta r do not have equal surface areas because these are curved surfaces, cylindrical surfaces. In a Cartesian coordinate system, the opposite surfaces both had equal area. Okay. So, there is the difference in this case. So, in general, for mass and energy, okay, the equation in a cylindrical coordinate system for the field variable is of the form partial phi field variable by partial t is equal to minus partial by partial r minus r times phi field variable plus s. I am sorry, r times not the field variable, but rather the generalized flux, where phi Fv is concentration or temperature, J is the mass flux or the heat flux, S is the mass source or the energy source by rho Cp. And using constitutive relation, okay, J is equal to minus alpha times partial phi field variable by partial r. Okay. Rather than alpha, I will write this as the generalized diffusion coefficient. Then my equation for the field variable becomes of the diffusion coefficient r partial of phi field variable by partial r plus s, and if the diffusion coefficient is also a constant, partial of phi field variable by partial t is equal to d by r plus s. Okay, so, there is the general form of the equation, okay, in a cylindrical coordinate system, in contrast to the Cartesian coordinate system where it was partial phi field variable by partial t is equal to partial z square plus s. This one was partial phi and this expression was and here I should note that this j is in the r direction. Okay. This j is the flux in the r direction. Okay. So, that is the difference. What about momentum transfer? So, in a pipe, for example, let me draw an analogy with momentum transfer that we had done for a Cartesian coordinate system. Okay. In that case, what we had taken was two surfaces divided by distance h, and the velocity was in the x direction. The Cartesian coordinate system we used was x was along the flow and z was perpendicular to the plates, okay, and one of the plates was moving. The direction, the velocity direction of the plate was perpendicular to the direction of variation, that is, the variation velocity is in the z direction, whereas the velocity itself is in the x direction. So, we were writing an equation for the variation of x momentum in the z direction, and we had got tau x z as the force per area in x direction at surface with outward perpendicular in z direction. Okay. In this particular case, there are two directions that are perpendicular to z. Okay. One is x direction that I have shown here, the other is the y direction, which will be perpendicular to x and perpendicular to z. So, this would be the y direction. Okay. However, whether you have a velocity in the x direction or in the y direction, the two are completely equivalent. Okay. I could just substitute y for x and get all of the equations in this particular case, because this is a Cartesian coordinate system. All coordinates are equivalent to each other, they are all straight lines, okay, and surfaces perpendicular to each of these is a planar surface. Okay. So, whether it was x or y directions, it made no difference. For a cylindrical coordinate system, there are two directions perpendicular to the radial direction. Okay. Recall that I had said that this was the radial direction and this was the z direction. Okay. So, one possibility is to have a velocity in the z direction itself. Like in a pipe flow, you have a pressure difference and that causes a velocity in the z direction. Okay. So, in this case I have labeled the axis as x. So, let me just continue with that label. Okay. I could label it as z as well, it makes no difference, but in this case I have started labeling it as x. So, I will continue this. Okay. So, if I have the velocity Vx, okay, which is along the axis of the pipe, which is perpendicular to the radial direction. Okay. So, this velocity Vx is a function of r, okay, and Vx is perpendicular to r. Okay. So, you have velocity in the x direction, velocity variation in the r direction, which is perpendicular to x. Okay. I could have another direction of variation of velocity also perpendicular to r, and that is what is called the polar direction. Okay. If I had the flow between two concentric cylinders, for example, I have an inner and an outer cylinder, okay, both of them which have the same axis, okay, both of them which have the same axis. Okay. And if one cylinder rotates with one angular velocity omega I and the other rotates with an angular velocity omega o. If they rotate with different angular velocities, there will be a velocity that goes around the cylinder. Okay. There will be a velocity that goes around the cylinder. Okay. This is also perpendicular to the r direction. Okay. It is along the cylindrical surface, it is perpendicular to the r direction. This I will call as v phi along the polar coordinate. Recall that when I had started off, I told you that there is a third coordinate around, okay, which is this phi coordinate, which is in this direction. Okay. The phi coordinate is in this direction. Okay. So, that is the other possibility for the velocity perpendicular to the radial direction. Okay. So, these are two possibilities. The first one is observed in pipe flow. The second one is, for example, observed in flows between two cylinders, like if you have things like ball bearings and so on with two cylinders with a fluid in between for lubrication, then you will have this kind of flow, okay, where the velocity is in the phi direction, perpendicular to the radial direction and perpendicular to the axis. And these two have very different momentum conservation equations. Okay. So, I will just give you the equations, I will not go through the solution. Okay, in axial direction. Okay, the velocity is equal to Vx, okay, in the axial direction. In this particular case, the velocity is equal to Vx. The momentum conservation equation for the x velocity, which varies in the r direction, turns out to be exactly the same as mass and energy. Rho partial Vx by partial t is equal to 1 by r delta by delta r of r tau x r plus any body force in the x direction. Okay. Note that for the momentum conservation, we do not have a negative sign in the diffusion term, because tau x r is effectively the negative of the flux in the of x momentum in the r direction. This equation is for the x momentum, axial momentum, the transport of x momentum in the r direction, where tau x r is equal to force per area in x direction at surface with outward I will write this again, perpendicular in r direction. Okay, so there is a definition of tau x r, and the momentum conservation equation becomes rho partial Vx by partial t is equal to 1 by r d by dr of r tau x r plus Fx the constitutive relation Newton's law for the shear stress. I should stress that this conservation equation is only for a unidirectional flow. Okay, it is not for any general flow. This is only for a unidirectional flow. Okay. And then the equation becomes rho partial Vx by partial t plus is equal to you can divide throughout by the density. Okay, so I can just take the density to the right side, I can divide throughout by the density. If the density is a constant for an incompressible flow, right, this becomes incompressible r times the kinematic viscosity partial Vx by partial r plus Fx by rho, okay, where nu is equal to the kinematic viscosity, that is the ratio mu by rho. Okay. Nu is the kinematic viscosity, which is the ratio mu by rho. Okay. And further, if the kinematic viscosity is a constant, the equation becomes partial Vx by okay. So, these are the momentum conservation equations for the axial momentum. Okay. These are the momentum conservation equations for the axial momentum, and they can be derived exactly the same way as the mass and energy conservation equation. They have the exact same form as the mass and energy conservation equations. Take the energy conservation equation, substitute Vx for the temperature, the momentum diffusivity or the thermal diffusivity, and the body force density for the source density, and you will get exactly the same equation. Okay. My apologies, this should be rho. Okay. It should be density, where Fx is the body force density in the x direction. Okay, the body force density in the x direction. Okay. So, this is the axial momentum conservation. Okay. What is the momentum conservation equation? In the polar direction. Okay. Recall that the momentum conservation in the polar direction corresponds to a configuration something like this, where you have, for example, two concentric cylinders, okay, of different radii, which may be moving with different angular velocities, omega I, omega O, okay, and you get fluid flow around the axis. Okay. This was the velocity v phi. Okay. You get fluid flow around the axis. The velocity was v phi. Okay. In this case, what is the momentum conservation equation? Okay. For the axial velocity v phi. Okay. I will not derive it, I will just give you the final result for the momentum conservation equation. Okay. The final result is rho into partial v phi by partial t is equal to, or I will just write in terms of kinematic viscosity. This expression I am writing only for the case where the kinematic viscosity is a constant. Okay. This I am writing only for the case where the kinematic viscosity is a constant. This will be nu d by dr of 1 by r d by dr of r v phi plus f phi by rho. Okay. This is the equation for the case where the kinematic viscosity is a constant, where nu is the kinematic viscosity, v phi is the velocity around the axis, and f phi is the body force density in that direction. Note the difference between these two. This is the differential operator for v phi. Okay, d by dr of 1 by r times d by dr of r v phi. Okay. This is the operator for the axial velocity, 1 by r d by dr of r d by dr. Okay, that is this one. Okay. So, the two are different. That is because v phi is a velocity along a circle. Okay. So, even though the magnitude is the same, as the fluid moves along the circle, the velocity vector changes because the direction changes. Okay. Okay. So, because of that, whereas when a fluid moves in the axial direction, even though if the magnitude is the same, then the vector is the same because the direction does not change. Whereas in the case of the polar velocity, the magnitude can remain the same, but because the direction changes, the vector changes. Okay. And that is something that has to be incorporated in the when we do the derivation. that is outside the scope of this course and I will not pursue it here. I will also say that tau phi r, okay, is equal to force per area in the phi direction. Okay. So, if I look at this pair of cylinders from the top, okay, I have an inner cylinder that is moving with some omega angular velocity. The outer cylinder could be moving with a different angular velocity, okay, and the phi direction is along the along a circle. Okay. So, the phi direction is along a circle, the z direction is perpendicular to the plane and the r direction is radially outward. Okay. Tau phi r is the force in the phi direction at a surface whose outward unit normal is in the r direction. Okay. It is the force in the phi direction at a surface whose outward unit normal is in the r direction, that is at the cylindrical surface. Okay. At a surface with outward unit normal in the r direction. Okay. And the expression for tau phi r is also different, okay, is equal to the viscosity into partial V phi by partial r minus V phi by r. So, this is not just the simple expression we had for tau x r. Okay. If you recall, we just had the derivative for tau x r. Okay. Whereas for tau phi r the expression is different. Okay. It is equal to mu into partial V phi by partial r minus V phi by r. Okay. So, both the expression for the stress and the differential equation are both different for the polar component of the velocity. Okay. It's the axial component, the balance equations and the equation for the stress are the same as what you have for mass and energy conservation. Okay. For the polar component it is different. Okay. So, now that we have solved this, got the equations, then we can proceed to look at steady state solutions. Okay. No variation in time. So, 0 is equal to minus of r alpha partial t by partial r plus energy source by rho Cp. Okay. And if there are also no sources, steady solution constant diffusivity. Okay. Then this is of the form 0 is equal to alpha by r d by dr of r partial t by partial r. Okay. And in general you can divide throughout by alpha, so you just get 1 over r. Okay. So, this contrasts with, for the Cartesian case, 0 is equal to partial by partial z of alpha partial t by partial z plus S e by rho Cp. Okay. Or 0 is equal to alpha partial square t by partial z square, constant diffusivity and no source. Okay. So, these are the equations. So, for the Cartesian coordinate system, for which the equations are shown in red, at steady state the solution is that the temperature is a linear function of z. Cylindrical coordinate system, that is not a solution. Okay. You can easily verify that. What is the solution? I will come back and I will discuss in the next lecture. I will see you then.